So today I'm going to get started by talking about forces. It's the push and pull that changes the state of rest. There's thrust, drag, and torque. Thrust is something that increases velocity, drag decreases it, and torque changes rotational speed. There's tension, which pulls things apart, and compression, which pushes them together. The mass weight is like mass times density times mass equals density times volume. Density being the measure of the mass within the volume, mass over volume, and volume is the space occupied by the mass. Mass is the amount of material the body contains. So reactional forces are pretty much just how something reacts to a force that's pushed on it or pulled against it. So like this slinky, like because I have tension on it, it sags down. Its reaction is to sag, is to bend. Whereas I don't know, like this cup, if I push on it, then there's no there's no reaction at all. Or the water, if I put my finger inside of it, then it would push down and flow around it. So this is a pretty simple force diagram. It's just kind of showing right here the force that gravity puts on the object that pushes it straight down towards the center of the earth, the normal force that acts down on it and pushes against it, and the shear force. So like a 15,000 or a 1,500 gram block sliding down a ramp, it's a pretty basic physics equation, figuring out the forces that interplay and act on it. So moving on, we'll go down to forces in the subsurface. So in geology, you would deal with two kinds of changes in forces. There's geologic time changes in acceleration, which is like a plate boundary moving over, meters or, tens of meters, and how long that could take. It could take millions of years, to move something, 12 miles, to the east or something like that, because it's going like 6 centimeters per year. Or there's short-lived, which is immediate, like an earthquake or some kind of like landslide or something that happens right away. Body forces and electromagnetic forces. So a lot of the immediate stuff happens because of gravity, So like body forces act on the mass of the body depending on the amount of material of the body. So like if you hit a sledgehammer against, like one pebble, then it's going to bust into a whole bunch of small ones. But if you hit a sledgehammer against like 2 meter, like or I don't know, like a mile by a mile, area of rock, it's just going to chip the surface. It's not going to have as much change on that body. So contact but the independent forces created by adjacent surrounding materials. So like I guess this one's more talking about like if you have a giant mass and you push down on it, then the surrounding material might change the way that amount of force acts on it, which is kind of like the sledgehammer analogy. Like if you hit a small rock, then there's no real forces around it, and the competency of that small pebble is going to cause it to have, pretty much just break apart immediately. But a larger mass will just kind of, because of the other forces that are pushing against it on all sides, then that little bit of force from the sledgehammer is not going to do much against that huge body. Contact forces push or pull across real or imaginary surfaces, and that's kind of difficult to think about when you're thinking about like imaginary surfaces versus real. An imaginary surface would be like an electromagnetic field, which has like a never-ending it's kind of difficult to explain. Like if you focus in on one point in space and then expand it, in theory, like if you expand it to infinite lengths, then that electromagnetic force has an unending distance in the up and down, which would be kind of the imaginary surfaces. But a real surface would be like the surface of a table. Gravitational force is responsible for a large amount of microgeology, so that kind of short-lived, instantaneous, and small, like minutia kind of stuff, like cellular level kind of things. Not not cellular, but microscopic. But influence of electromagnetic force can alter a solid material at a submicroscopic level to allow solid rock to flow along margins. Loading, gravitational loading is the pressure of ever-present gravity lithification. So, like, as material gets buried deeper and deeper, the amount of force increases on it with the weight that is upon it. So, like, something directly at the surface isn't going to have as much force on it from gravity as something 10 miles deep, which has all of the rock pushing down on it. Thermal loading, heating or cooling in rocks, creating forces within the rock body. So, like, if you heat up a rock, like, it's going to move particles around depending on where the heat is. Displacement loading, force through mechanical processes. So, like plate tectonics, like something changing in position in relation to something else. So plate tectonic forces, the pressure applied to separating plates. So this is kind of like, this is a good view of it, is kind of depending on where you're at in this diagram, like this is like the ridge pushing against it, so like the ridge resistance of it, and this is the what is that? That's the ridge push. So this is like the amount of force going that direction, and this is the amount of force that's resisting that push. This is like down up here is the FSU is the trench suction, so that's like pulling it down kind of, and then the RO should be like the resistance of the overriding plate, so that's like pushing it back up. It's just kind of showing a diagram of the interplay of forces just within one geologic area, and how you have to consider a lot of the different stuff that's going on. Like this right here is the negative buoyancy. That's like how something is kind of being pushed down into it. Like if you have silly putty and water, and you're pushing silly putty and water together, just on tabletop, the water is going to override the silly putty because the water has more buoyancy, or it's a lighter material. Mantle drag is the resistance from drag. Slab pull, which would be FSP, I think, right here. That's the negative buoyancy from temperature differences, and it acts in the vertical. So let's see. Tractions is pretty cool. It's the force that considers the amount of area it interacts with. So like, if you put if you have a sheet of paper and you put okay, like here, I guess my notes should suffice. So the amount of force spread over an area is not as much as the amount of force that's spread whenever it's just in one point. Like, so like if you have coal in a diamond, and you have so much force over one area, then the compression's not going to be as much as if you just, it's a Star Wars video, but if you have like just a bunch of force in one area just pushing straight down. So this is like just showing like how it interplays at depth. 35. So stress will deform the body if the strength of the body is exceeded. So a strength of the body is pretty much just like, I don't know, I'll just have stuff on my desk and see if I can make an example out of it. I'm going to make an example of you, and sticky notes will work. So like the strength of a body is like a sheet of paper, right? Like the amount of force that it takes to cause it to rip, that the sheet of paper has a low strength, but like I can't really rip my slinky, like the metal coils. I can't rip that because it has a high strength of the body. So my force doesn't exceed the strength of this body, the competency of this material, but it can exceed the competency of this. So traction is the vector quantity of stress that is expressed through simple shear. So like I don't know, like I guess the best way to kind of think about it is like, you know, like if you're walking along, you know, the surface, your feet have traction against the surface, but like here, you know, a clockwise shear is considered positive, and a negative shear is considered negative. Counterclockwise is negative, and you know here the T down and T up is positive, and T up going up and T down going down is considered negative. So like this would have a positive traction, this would have a negative, this would have a positive shear, this would have a negative. I don't know if that's the same in the camera. Can't tell. What did I say? This is. Let me see real quick. So this is positive. Is that clockwise or counterclockwise? I'll watch the video and figure it out. So like stress considers forces in all directions. This is kind of like when you're considering stress, you know, like in a body at depth, you have to think about it kind of like in space, you know, or it's in a three-dimensional plane. It's not just like, oh, it's pushing down, so it's just going to squish down. Well, when it squishes down, it squishes out, but it doesn't just squish out, you know, like towards and away from you. It squishes out, you know, to the left and the right and at angles, you know. So you have to think about how the forces interplay in a three-dimensional space, which sounds a lot more confusing than what it is. You know, it's just kind of thinking about something like if you squish down on dough on a countertop, the countertop's pushing up against the dough and your hand is pushing down, so the dough will go in all directions. It's kind of the same thing with rocks and geology and depth. If you think about it like baking dough, it usually makes it a little bit easier. Talents forces given by a single point. So like this is basically just saying like if you have one point in space and you have something pushing down on it and pushing to the left on it, then it's going to go down and to the left. Like that is the overall direction that point is going to take. You have something pushing down to the left and to the and up, but the up direction is less, then it's going to go down and to the left just slower. So that's kind of what it's talking about there. I think I'll save joints for next time though.